Rational functions. We won't be able to finish all of it, but we'll get as far as we can in about 25 minutes. So, learning objectives, find the domain of rational functions, find vertical, horizontal, and slant, graph rational functions. So, the first bullet point, we've talked about a ton, domain of fractions. Then new stuff are the asymptotes, and then graphing is a collection of a ton of information. So we'll start off with just a picture. A rational function is a function that can be written as the quotient of two polynomial functions, p of x and q of x. So f of x is equal to p of x divided by q of x, where q of x, of course, cannot equal 0. So here, this is an example of a rational equation or function. Okay, these right here we'll talk about later are vertical asymptotes. Everyone says I say asymptotes funny. I can't hear it, but everyone says it. Even students who feel like they're not strong at math, they're like, you say that funny. I'm like, that's fine, I'll take it. I literally cannot hear it. But anyways, these come from where the denominator is equal to 0. Come from denominator. The noms. You have x-intercepts that come from the numerator. Okay. Come from the numerator. And then here it says horizontal asymptotes. This comes from the ratio of your P's and Q's. Okay. So horizontal asymptotes comes from the ratio of the P of X and Q of X. We'll get to more into that later, but just to kind of give you a heads up as to what's happening. So this is saying like left and right, what's going on. So horizontal asymptote is the equivalent of end behavior from polynomial functions. For rationals, we call it end behavior. Okay. So quick review. Remember that for fractions, our red flag, right? Our red flag is that we can't divide by 0. Can't divide by 0. Okay, that's the red flag. So we always factor the denominator, see where things go haywire. So taking the denominator equal to 0, subtracting the 2 from both sides. So then x equals -2. So now this is the number that gets kicked out. So we have -infinity to -2, union -2 to infinity. For those of you who liked the graphical, right, that basically has the number line shaded everywhere except at -2. That's the domain. So for B, what we want to do is factor. We want to factor the denominator. So this is equal to, let's see, x times x, and then 4 and 2, because those are the two numbers that multiply to -8 and add to -2, specifically with 4 being negative and the 2 being positive. So we set this equal to 0 and solve. So x plus 2 equals 0, x minus 4 equals 0. So subtract 2. So x equals -2, add 4, x is equal to 4. So now there's two numbers that we are kicking out. So here's -2, here's 4, open circle, and then everywhere else on that number line is filled in because we exist in all places except these two. So I have -infinity to -2, union -2 to 4, union 4 to infinity. Hopefully this wasn't too challenging, right? We've talked about domain at least 3 other times at this point. If it is challenging, please come find me. Okay, vertical asymptotes. So the line x equaling c is a vertical asymptote of the graph of the function f of x. If f of x approaches negative or positive or negative infinity as x approaches c from either side. Okay, what the world does that say? That says if I have some graph that looks like this, here's c. I am a vertical asymptote. That means I am a wall that I cannot cross. A wall can't be crossed. Okay, you can't go, no climbing over, no going under, no going through. Okay, no dice. Can't do any of these things. Because, like I said earlier, they come from where the zeros are in the denominator. We cannot divide by 0. So therefore, we cannot touch this wall. So I'm a function. And I am, or say you're a car, you're driving, you come to a wall. Well, you're forced to either go up, or let's say you're forced to go down. Either case, you can go up or down, right? But you go to this wall, you don't want to slam into it, you got to choose a side. You go up, down. That's it. That's what we mean. Okay. So things that we want to do is we always want to reduce f of x first. Because if I have something of the sort of saying like, I don't know, y equals x squared minus 4 over x squared plus 2x plus 3. Okay, well, the numerator is a difference of squares. So that's plus or minus 2. The denominator is x minus 1. And then, let me change this to a, let me change it. Yeah, because that's a 1 and a 3, and I need a 2. This is what happens when I make it up on the fly. Let's see. Okay, let's see here. X squared minus, let me just make it easy. X plus 2. Just say it's x plus 2 over x plus 2. Then those cancel out. And we actually treat this graph like x minus 2. Okay. That's a minus 2. So notice here, this doesn't have, so this graph, no vertical asymptotes, but it has what we call a hole. So for this, if I vertical asymptote at 2, we treat it like, negative 2, pardon me. You have a hole. That'd be an open circle right here. Okay, that's what we mean by a hole. It's literally as if there's a hole in the graph. Okay, if there's a hole in this graph, it's as if someone took a push pin and just popped that part of the graph away. So we always want to reduce it first. So then zeros or any common factors are the locations of holes. There we go. That's what I was talking about. So find vertical asymptotes, if any. Notice if there's any holes. So 1, you always want to reduce first. Okay, reduce first. That's an exclamation point. All right, for example 1, nothing to reduce, so just set to 0 and solve. Add 1 to both sides. So x equaling 1. So we have a vertical asymptote at x equaling 1. So pictorially, like here's 1. We usually draw it with dashed lines to represent this invisible wall that we have. Next, we want to factor x, 36. What's 36 factors? 36 and 1. Let's see, 2 and 18, 3 and 12. Does 4 go into it? No. 5 go into it? No. 6 go into it? Yes. 7, 8. No, does 4 go into it? Yeah. Hello. 4 times 9. Silly goose. 4 and 9. And that's the one we need because 9 and 4 will subtract to give us 5. 9, 4 minus plus. Here we go. So we set each of these equal to 0 and solve. So subtract 9, add 4, add 4. Sorry, I'm doing this simultaneously. I apologize. It's probably not exactly how you want it. Forgive me. Yeah, so then we have vertical asymptotes at these locations. That's supposed to be an at sign. Pause the video and try C and D. Come back when you're ready. Okay, so for C, this is x minus 4 over x plus 4, x minus 4, because, right, that's the difference of squares, x squared minus 16. These factor out. So this really gets graphed like x plus 4. So the only vertical asymptotes we have are at x equaling negative 4, because we take the denominator, set it equal to 0, and solve. And then this last one, if we set it equal to 0 and solve, notice that we get a squared number equal to a negative, and that cannot happen. So here, there's none. No vertical asymptotes. That is practicing how to find them. They come from the denominator. Okay. Come from denominator. Vertical asymptotes come from where the denominator equals 0. Okay, we'll pause the video and we'll pick up with horizontal asymptotes.